my role here is actually to introduce our panel moderator, Zubin Jacob. So Zubin is currently the Elmore Professor of Electrical and Computer Engineering. He also has a courtesy appointment at the Department of Physics. He is a fellow of the Optical Society of America, and he was awarded the DARPA Director's Fellowship in 2019, the National Science Foundation Career Award in 2017, and the Purdue ECE Outstanding Graduate Student Mentor Award in 2018. His research is in the area of quantum photonics, materials physics, and AI, and his work has been featured on in many ways, including on the covers of both Nature and Science. So I'd like to invite Zubin up to introduce our panelists, who will then also be chatting with Shauni.
All right. So good evening, everyone. I'm very happy to see all of you here. First, I'd like to thank Milind for his very kind introduction. A few days back, Milind had emailed me saying, the title of the panel discussion is not done. And it was on my list of things, but it dropped often. And I said, okay, it was late in the night, and I thought, okay, what would make it fun on a Friday evening for all the students and faculty? And I thought, hey, you know what, maybe, yeah, future of nanophotonics, quantum, AI, and energy. And I'm very happy that our distinguished speaker kind of enjoyed the title of the panel discussion. And I am hoping that all of you who are sticking around for the kind of after party are going to also enjoy the discussion. Thank you so much for bringing in the chairs. The goal for today's discussion, we are going to try to keep it informal. We'll try to ask a few thought-provoking questions, maybe a few things about future directions, because we have very special list of faculty who have agreed to be on the panel. Right? So what we'll do is that I will introduce them, and then I will request them to kind of join me over here. I assume we will have a mic that will go between all of us, right? And I will try to stay away from your view of the panel panelists, right? Now, just so you know, on our panel, we have faculty from ECE and mechanical engineering. I have been given the responsibility of introducing them, but if I actually spend time introducing them, telling you about their accomplishments, about their awards, about how distinguished they are, we will probably be here till 4:30, right? So we don't need to do that. And for most of you in the audience, I think our faculty are extremely well known, but just for the sake of formality, I will quickly run through some of their kind of, let me say, very special contributions and abilities. And I have to say that, let me start with Professor Boltaseva. So if you are in the audience and you don't know Professor Boltaseva, you're probably not at Purdue, all right? So she is a pioneer in the field of material science, metamaterials, bringing in very new materials to solve nanophotonics challenges. And we are going to hear from her about all of these different perspectives, right? So we are really eagerly looking forward to this, and I'm very happy that Sasha agreed to be on the panel. She had to change quite a few things to be here, so we really appreciate that. After Sasha, I would like to introduce Professor Alam. Once again, a pioneer in nanoelectronics and also energy applications. So we have a very complementary set of kind of panelists here, and he has made many important contributions to biosensors, understanding fundamental limits of how these things work, energy devices, and also, importantly, solar cells. So that's a topic that we didn't really touch. Shauni has also made a lot of important contributions. We didn't touch on that, but in the panel discussion, we'll probably talk a little bit about solar cells and where maybe nanophotonics could play a role. So again, thank you, Professor Alam, for joining us. And then we have Professor Peter Bermel. He's an expert in solar thermophotovoltaics, and also in nanophotonics for photonic crystals, quantum applications. So we're going to hear from Professor Peter Bermel on both energy and the quantum side. And finally, we have Professor Shulin Ruan from mechanical engineering. And he is an expert on the computational aspects of both material science as well as photonics. More importantly, he's an expert in density functional theory, and he has also made kind of important contributions to radiative cooling. So I think it's a really nice opportunity to bring various different faculty together. I will try not to put them on the spot, but we will ask, and please feel free to ask kind of questions that you feel that are thought-provoking, futuristic, speculative. This is really an informal discussion Friday evening. I know it's beautiful weather, so I'm really happy that you've kind of sticking around for the fun part of this afternoon. So with that, I would like to invite all our panelists to the stage. And like I mentioned, I didn't spend too much time talking about their research areas, but we don't get time to talk to our own colleagues as often as we'd like. We distribute all across campus. We heard about the exciting stuff that Shauni is working on, but I thought this is also a kind of nice time for us to learn about what is it that our colleagues are excited about right now. Like, what is it that gets them excited in the morning to go to work and solve some challenging problems? So what I'd like to do is just to kind of warm up the discussion, I'd like to hear from our panelists and also from Shauni about what is the most exciting thing that they are working on right now, broadly in the context of kind of nanophotonics, maybe nanoelectronics, and why are they so excited about that problem? So I think this is a great opportunity for us to learn about what is it that you're doing today, maybe unpublished stuff or maybe like fun stuff that you're really excited about right now. So maybe I might put Professor Ruan on the spot. Okay. Yeah, and we will start with Professor Ruan, and Shauni, please jump in if there's something that you are working on that you didn't have time to present. We would love to hear more from you about what is exciting you today, right? So please go ahead.
So how many minutes do you give to me?
I would like to hear from you for many hours.
Oh, okay.
And probably my students are here and we'll find ways to collaborate, but maybe a couple of minutes to go through
I'll try to
everyone.
2 or 3 minutes. I will see.
Great.
Yeah.
Thank you so much.
Okay, so really thank you for inviting me to join this panel and listen to Shaui's great work. So I'm working on two extremely spectrum of research, very fundamental, understanding the photon physics, and go to very applied, developing radio cooling paints. So I enjoy this is because we use our model to kind of help drive our research in the practical side. So first, photon. The photon properties actually are very well related to phonons as well. So these are two very different particles. But if you look at the infrared, for polar dielectric materials, I mean, particularly used in paints, TiO2, barium sulfate, HBN, calcine, and so on, these are polar dielectrics. So their infrared response is related to how the photons interact with phonons, which is quanta of lattice vibration. So these two, I started doing them during my PhD, but I never thought one day I would work on paints, right? They're so applied. So we look at the sort of physics and using density functional theory to understand and search for new material and translate the knowledge now how we can identify better radio cooling sort of pigments. That's how we really inspired by our own simulation to look at barium sulfate, HBN, and the future material. For example, how to switch between the super white and super black material for a climate like here, right? We need cooling in the summer, but we prefer heating in the winter. In Florida, Texas, probably cooling will be okay, but here we need both. Sure, that's a very challenging problem, even especially if you want to make it scalable, right? Another question is that how we can make it colored, right? Colored material will be less effective in cooling. However, if we can get better cooling of our new color material compared to the commercial color counterpart. That's very exciting. So that's what I'm working now from the fundamental physics, try to inspire our kind of a scalable technology, and I really enjoy doing that. Thank you.
Great. Thank you so much, Sholin. So as I understand it, switchable from ultra white to really dark black for various kind of climatic conditions, right? And also maybe bring in color into the picture, because at the end of the day, all these buildings have very fancy colors that you have to make sure that you adhere to. All right. So thank you, Sholin. That makes a lot of sense. Peter, would you like to go next?
Sure. Can you all hear me?
It's not working. Yeah.
Let me try that. Is that any better?
Yeah.
Okay,
Yes.
great. Okay, so first of all, thank you so much for the invitation to join this distinguished panel of esteemed colleagues and scientists. There are so many exciting things happening in research. I can only touch on a small fraction of all the excitement, but two specific things I wanted to highlight. On the energy side, I'm very excited about a field known as agrovoltaics, which combines agriculture with photovoltaics. And the way that I think about it, being trained in photonics, it's really a photon management challenge. When you have sunlight as a limited resource, how do you allocate it most effectively to support providing food and water for everybody, as well as providing energy for the modern technology that we're using? And as many of you may know, our energy demand is increasing. At the same time, there are increasing stresses in our environment. So if we can maintain the right balance between increasing renewable energy generation to reduce pollution, but then also still produce the food and water resources that we need to live, then that would be fantastic for our future sustainability. In terms of how we're doing that, so there are a lot of different ideas that we're working on. Some of these are actually just theoretical in nature, and some are actually being done in the fields nearby Purdue in what's called the Acre Farm, about 5 miles from campus. And so there we have one test site that's already in operation for the last few years. We've collected data to show that corn and soybeans right below photovoltaic panels can still grow about 90% of the crop yield as in an open field. And then we're also building a new generation that's using modern bifacial single-axis tracker technology that's actually commercially relevant technology, using also new types of corn, which is called short corn. And it turns out in a preliminary trial from last summer, it had nearly the same yield as full height corn. So that's actually really interesting technology for the local region. So then going on to the second topic, another topic we're really interested is in the quantum realm. So we're particularly interested in topological insulator materials. And some of you may have heard of those and some may have no idea what that is. But the reason why they're interesting from a quantum perspective is that they are more robust to individual atoms being impacted by local noise and variations. So many of you have probably heard of Schrodinger's cat. And so you may know that Schrodinger's cat is kind of like a fictional construction at the macro scale, but at the nanoscale it can exist. But in order to maintain that cat-like state where you actually have two or more different states, then you actually need something that's robust enough so that you can interact with it, but it won't be destroyed by that process. And so that's like something that topological insulators are particularly promising to achieve. And that's something like there are actually a wide range of materials that we can build in the labs at Purdue and also at some nearby institutions that can actually generate those topological states, and they can also be modified by external factors, including electric and magnetic fields, which are associated with light. So that's kind of why I'm interested in that. So that's at a high level things we're working on.
Great. Thank you so much, Peter. So just to clarify again, did I hear it correctly that you said agrophotonics?
Yeah, agrovoltaics, and we're using photonic technology to actually filter the wavelengths of light that are going to different parts of the field. So just to give you a simple example, and I'll be brief, if you think about the way that crops grow, they actually use what's called photosynthetically active radiation, 400 to 700 nanometers. But photovoltaic cells can actually use a much wider range of light, including ultraviolet and infrared. So if you make sure that the crops get all the visible light, then you can reuse a lot of the other light for PV generation.
Okay. Very nice. So for some of you here, I mean, these are terms which are new to me, but the probably terminology that you'll hear in a few months as the next hot topic coming out, maybe agrovoltaics, agrophotonics. I think this sounds a lot of fun to me, and it's the first time I'm hearing about it. All right, thank you so much, Peter.
No problem.
Right. So Shauni, would you like to tell us about something exciting you're working on that you didn't have time to tell us, or something unpublished that we could jump on before the rest of the world does?
Sure, yeah, I can maybe say two things that we're actually quite excited about. This going back to my own roots as a theorist. My group is actually mostly theory group, so we're generally interested in theory topics. In nanophotonics, one of the things we are getting to be quite intrigued about is how you do simulations. Of course, all of us do. If you look at the field that's generated, one of the things that you realize is that it's not random noise. If I show you a field pattern, you will know it's a field pattern. If I show you a random noise image or your image, you will know it's not a field pattern. Now, so there are intuitions associated with it. Or the statement to phrase it is that there are lower dimensional representation of the field that we actually don't exploit in our current numerical method. If you think about our current numerical method is to discretize space, that you have a little bit of information, but not much, and almost none about the field distribution. If I have a uniform grid, essentially it's as good to represent a field distribution as to represent an image of you, as to represent random noise. So and I think this is an area where many of the idea from machine learning can be actually quite interesting in combining that with computational electromagnetic to enable faster simulation. Yeah, so that's maybe one I would mention that I'm quite excited about. The other one we actually recently get into, again, is a very basic work, is to generate a very unusual state of light in free space. Now you say, well, what can you do in free space? It turned out, and this is known for a long time, that there are many unusual solutions that people have not really demonstrated. One of them is that, in fact, it is possible in free space to have a wave packet that propagate at any velocity, okay, and that doesn't spread.
Okay.
This is known for many years, but there has been some demonstration with very, very complicated setup. But we have looked at using very compact photonic structure for its generation, and we are now starting to see those experimentally. So I brought those, which are more basic topic, and I think they are actually quite interesting and may, down the road, point to new possibilities.
Thank you so much, Shauni, for that. Gives me questions that we can address later on. Maybe the noise you mentioned may have some connections to diffusion models or variational autoencoders. So we'll be very happy to discuss that during the panel discussion. So next, we'd like to go to Sasha and hear what's the most exciting thing Sasha is working on.
Thank you. Thank you so much. And first of all, thank you for inviting me to join this panel. And when you send the questions and like, what's exciting stuff you're working on? I thought, well, that would be hard because definitely we don't work on anything which is not exciting to us. So, but with this said, I want to paint like a broad picture of what our amazing photonics team is doing. And co-led with my dear husband and colleague Vlad, and there are many team members here, so we really feel like a family that are, pushing big things forward. And So what we're trying to do, knowing from history that real breakthrough and exciting things, the truly exciting things happen at the intersection of disciplines, that's what we're trying to bridge together. So all things nanophotonics would be of interest to us, but specifically the intersection and leveraging the expertise and recent breakthroughs in material science, quantum science and technology, and AI. That's what we are trying to bring into photonics, and that's where we're trying to bring photonics in. And I will just give you a couple of examples for each of these directions. So material science, and you mentioned already that my team has been working with material platforms and photonic materials for a long time. And what we're interested in addition to just making photonics practical, which is also important, and I believe we'll be talking about the chip scale stuff later, but materials surprisingly can unlock totally unknown physics and totally new regimes of operation. And so one example would be materials that can allow for ultra-fast and extremely high modulation. So we know, there's always trade-off. If you modulate something fast, the signal changing just a little bit and the other way around. So why interest in these materials? Well, we can think about some exotic states of matter like photonic time crystals. Thinking about materials that can have different regimes of localization. So they're interesting from the photonics perspective, but they also maybe unlock some interesting regimes for electron behavior. Strong localization and how this would interplay with photonics functionalities. Ultra-thin films, materials that are really high temperature stable, getting back to energy, right? Whether we have amazing concept, we need materials that would be able to withstand high temperatures for energy conversion. So all this fits into kind of bringing material science into nanophotonics. Now, quantum, all things quantum and their intersection with photonics is a prime interest to our entire team. And we have a flurry of activities. So Department of Energy funded National Quantum Initiative Center. We have new FRC. And again, we came to this field with a background in nanophotonics and our understanding of how we, for example, can control the emission from quantum emitters, right? So now what we are trying to do is how to push the quantum technologies further, knowing that photonics is this amazing approach that can guarantee in the long run scalability, robustness, and low power consumption. So working with quantum emitters and trying to see how we can control them and eventually put them on a chip for application in quantum sensors, quantum photonic computing, and quantum communication systems is another one. And we are interested in many things quantum. So Vahagan, for example, is working on a very exciting project of how we can model the topological quantum states, and that's going, also some of the things already mentioned, and some of the interesting things around how we can mimic these topological quantum materials in many systems, including photonics, is also of interest to us. And then AI. AI is everywhere, and as I always say, there is no field in engineering right now that is not using AI. And if they don't, they are behind, right? So, goes both ways. How we apply machine learning in classical way and AI in conventional way to improve the performance of our devices, and where are the breakthrough there, and how we can apply photonics to advance AI, and that's what our speaker was talking about. So that's some of the directions that we are very much excited about.
Thank you so much, Sasha. So we have kind of three big areas that we will be talking about: AI, energy, and quantum. You can have this one. You can have one all for yourself, please. Yes.
All right.
So,
thank you for this opportunity. I work on, among other things, on solar cells, and solar cells, of course, is interesting for many reasons. because this is a prototypical system where you are interested in nanosecond timescales, where electron hole recombination or photon recycling, all the way to decades-old issues of reliability, because you have to operate in 40, 50 years in a desert environment or environment and on the other hand, you are also interested in nanoscale defects, but then you are also interested in systems that spans many, many kilometers, large-scale solar farms. So this is a fantastic system that spans 14, 15 orders of magnitude in space and time. But most recently, I've been working on two things that essentially tries to answer two questions. One is, can you cool a city by using vehicle integrated or city integrated photovoltaics? That is, you could think about a city where the cars are like atoms that can absorb light. And if it can absorb light, many of the cities these days, one of the challenges, cities are getting very hot, and cooling them has been a concern. And increasingly, about 60-70% of the population will move towards cities because of various reasons. And if you can absorb solar energy as a vehicle integrated way and design the facades of the cities just like what Professor Fan was talking about, then you can essentially absorb them, store them in the battery, and take them away in the afternoon. So like phonons, the cars as a phonons. So that takes things away, and you can easily show that you can have 2 to 3 degrees reduction in the city temperature just by integrating photovoltaics in the facades and in the car. The other question I'm trying to answer is, can you read the heartbeat of a field-deployed electronics? And there the idea is that most of the electronic devices, whether these are photovoltaics or the cars, electrical vehicles, or any field-deployed electronics, everything dies over time. Everything degrades, everything, just like us. Over time, we get old. The thing is that you cannot go in and check each individual. You have kilometers of solar farms. How are you going to ever understand which part is degrading, how to sort of find out which needs replacement? Same for electrical vehicles. Same car running in Florida versus car running in Alaska is going to degrade completely differently. How are you going to predict this? It turns out sun is a global clock. Every morning, the solar cell executes the same periodic motion. And so therefore, there is this periodic signal. And if you know how to read the periodic signal of your toaster or your washing machine or your solar, then essentially lies within it. And if you know the physics, that how are the components degrading and how do you make a better technology? So in short, just thinking, connecting small with large, those are the things I'm thinking about.
Thank you so much, Ashraf. This was very nice. I think that this opens the floor for discussions. And I think what we'd like to do is, since we are on the topic of energy, I think we should have a couple of questions on energy, and then we'll go to talk about AI as well as quantum. So we'll try to add in everything in our kind of half an hour that we have. But maybe we'll start by discussing the idea that Ashraf just mentioned about cooling cities, right? So what I want to know is, so let us assume, for the sake of discussion, that Shauini's radiative cooling works, Shulin's approach of having different colors, the switchability works, and Ashraf's approach of really looking at solar cells and the cooling works. Like, these are lab demonstrations, and let's say all of this works. My question is, what prevents the widespread adoption of such technologies? So how much time will it take from, say, lab to really making this transition? And is it, so I'm just thinking off the top of my head, is it is it cost that limits these things, or is it regulatory bodies? Like, how does a professor or a student really go beyond the thought process and go and take it to the real world? So I wanted to know your thoughts, your experiences broadly from this about this energy crisis in some sense. Yeah. Who would like to go first, please?
I can briefly start. When I did my PhD, I worked on semiconductor lasers, and I thought I have a very good understanding about how lasers work and all. And then I joined Bell Labs, and it didn't take me 1 month before I realized that I only know a very niche part of the whole thing. Because it is one thing to understand a device, another thing is to understand a system, another thing is to understand the deployment. I think in academia, for good reasons or bad, we have tend to focus on very narrow aspect of the thing and solve a problem with the narrow boundary conditions. For example, many of the things that we have to worry about in degradation, for example, even the emitters we are talking about, if there is soiling, then how do you clean the soiling? When you clean the soiling, will the coating go away? These are the things people worry about once you want to get to the system. So I think it's not regulation or other things. Those are, of course, barriers. It is a lack of our, broad scale understanding about the system and what the system needs is, I think, what prevents these systems to get into actual demonstration quickly.
Yeah.
Sasha, go ahead, and then Shauni.
Okay.
Yeah.
Oh, you want me first?
No, I said Sasha first, and then Shauni.
Okay, sure. I just want to add a little bit to that, and I think that's a beauty of academic world, that we can actually choose our problems wisely, right? And that's one of the motivations why we started to look so much into materials, because in photonics for a very long time people just worked with something that was well established, and didn't think about potential technology scale up or how environmentally friendly or conflict-free, you name it, the materials are. And it's important. As I said, there are so many beautiful fundamental concepts and highly efficient designs or theories that predict the performance of your, let's say, plasmonic or metal-based structure. But then if you think about the operation, you say, hey, okay, it's not extreme environment, it's not high temperature, but even at room temperature, when you run this device, it will heat up. So it will be actually local temperature rise, and it would be dead within a few cycles of operation. So it's important to take this material aspect into account, and also how receptive the industry will be. Like, they're not going to change all production lines simply because you came up with a breakthrough idea that this specific exotic material performs better. No, because it's just too hard and too expensive. And final thought I want to add, in addition to the life cycle of our devices, we have to think about afterlife. And that's becoming an increasingly important problem worldwide. What happens with all the devices we make afterwards when they're, out of the fields?
So, Shauni, would you like to add to this?
Right, yeah, maybe I'll just add one thing. Those are also very, very interesting points on new materials and on these big problems of urban heat islands and so on. One of the things that I've been thinking about, especially on the energy side, is that it is actually very important to understand how you make money with your energy technology and make it as much as you can. This is, so in other words, what exactly is your business model? Who are you going to sell the technology to? Who is going to pay for it? And why are they paying for it? This question, I actually think has a lot of intellectual depth. It sounded like because one actually need to think through on these things. And what make, especially on the energy side of things, one need to deploy it at scale. That's very different from the lab scale demonstration. And being able to take the technology to scale, one really need to figure out what the market really is saying. And that's something I think that's actually quite challenging in this field.
Well, thank you so much. Those are also words of wisdom for everybody to think about as we are thinking about technologies, right? Eventually, what would the business model look like, and who should care, and why should they care also? I think that's also great input. Peter, please.
Yes. So I agree with all the comments made by my colleagues, but I did want to add one other point, which I think is important, which is acceptance of society. We have to really be mindful when we develop all these technologies that in the past there have been some technologies that have been deployed in ways that were not leading to good outcomes for many people. And we need to be mindful of what are all the potential consequences, both intended and unintended, and how do we mitigate all those risk factors, and also provide data and evidence to assure anybody that would be impacted by these technologies that this is providing a net benefit to them personally. Because when you talked about permitting and regulation, that comes back to people. Do people accept these things? If people accept them, then regulation will be aligned with that. But if people do not accept these technologies, then we'll have a resistance, and then we won't be able to see adoption. Even if these are fantastic business plans and they're fantastic technologies and they would improve the world, but if we can't assure people and make them believe that, then we're going to get stuck at that point. So we do need to also take that into account.
Completely agreed, Peter. Thank you so much for that. Shulin, you had a few things to add?
Sure.
Yes?
Sure. Yeah. I agree with all the wonderful comments already made by the panelists. I mean, they really resonate with my own experience. Okay. So it does take time and transition from a concept to initial prototype and then to a real product. I mean, our work was inspired by Shanhui's early work in 2014. Actually, that's when we started. I mean, to pursue paint's approach for radio cooling. Now, over the years, we kind of resolved many technical challenges, like the dust is a problem, how to keep them clean. Usually industry would think porous paints are not good quality paints, and they accumulate dust, and how do you resolve that? I mean, this can be resolved. And but then on the business side, I totally agree with that. Now, these days, I'm thinking about the supply chain, even tariffs. For paints, the most cost-effective will be natural minerals, right? Whether these are mined in Europe, in the domestic, or in China, that greatly affect the price. So yeah, as our technology is progressing on the way, the challenges we're facing are different. We need to resolve one by one. Maybe the last one, the hard lesson I learned that. I initially work with big companies. They are very good. They are very engaged, but they are also kind of scared and slow. So I'm myself is ramping up more to develop technology within my own group and potentially a startup company. I'm still engaging with big companies. There's big stakeholders, and then they can be serving in different roles. So yeah, thank you.
Thank you so much, Olin. So what I'd like to do now is maybe open the floor for questions related to energy, related to some of the points that was just mentioned. There's a lot of challenges in going from your lab demonstration to really the world at large and make that real world impact. So for the students who are listening, I mean, this is never too early to be thinking about all of those things beyond just the papers and the theses, right? So let's see if there's any comments, questions to add broadly in the energy discussions that we've had so far. Milan? Okay, yeah, we wait to hear from the students who seem to be very shy. If nobody asks, then I'll pick on my students, because they cannot complain. Yes.
Hey, my question is for Professor Bermel. Is using fluorescent material a promising approach with agrivoltaics? Or, yeah, that's my question.
And materials. So one actual interesting technology that's closely related to that, it actually is basically using the concept that you can actually bring in light from like a kind of a semi-transparent structure, and then you can send it to the sides. That's actually called a luminescent solar concentrator. And so it may not be fluorescent per se, but the idea is similar. So it absorbs infrared and then it re-emits at a different direction. So that's a very interesting topic. There's a lot of people doing research on that. So you can use that in potentially building integrated PV as well as like agricultural applications. Obviously, one of the questions that we're investigating, not just our group, but many people in this field, is would it be more effective to use a luminescent solar concentrator, to use like a more conventional so-called non-imaging optics concentrator, or to use other techniques to harvest the infrared light selectively, right? So there are essentially dozens of potential technologies that we're considering. Another technology we're looking at is called a diffuser. So in the context of agricultural photovoltaics, diffusers are probably one of the simplest technologies, but the reason it's interesting is the response of plants to reduction in sunlight is actually nonlinear. So if you can actually spread light uniformly below a PV panel, then you can get overall higher production than if it was like very deep shadow right below. So that's actually like the easiest technology because you can buy it off the shelf. But luminescent solar concentrators could be very promising in future development. So I hope that answers your question.
Thank you so much, Peter. Any other questions?
Yeah, I actually wanted to ask maybe a little bit of a meta question, and I'd maybe direct it to Shauni first because you're our distinguished guest. You guys all kind of spoke, and Peter, I think you really highlighted it too, about the importance of public acceptance of the kinds of things that we're trying to do, right? We build these new technologies, especially in the space of energy. A lot of these new technologies are affecting the built environment in very visible ways, which means that they can often attract a lot of public attention. What role do we, and I might ask to phrase this as, what advice would you give to students to think about how they communicate the things that they are doing to maybe help the public understand what we're doing and the value of what we're doing?
I should say maybe I would talk about one of my own experience. When we, it's not necessarily to public, but it's more to industry. When we did our radiated cooling work, ARPA-E, which is one of the DOE agencies, wanted to give us money. But one of the preconditions they did was that we have to go through startup training. So this is the NSF I-Corp program that some of you may know. So I went to, with Ashwas Raman, we went to DC to get I-Corp training. And one of the things they teach you is that you got to talk to customers. And their assignment at the time was within 3 months, you have to talk to 100 customers. Ashwa did most of the work, by the way. So it's good to have good students, I must say. It's all the credit to him. But I went through some of those interviews, and it was quite eye-opening to go through the interview to listen to what they think about technology and why they adopt or not adopt a technology. And it could be very, very different from what you have thought about in your office, in the lab. So I think, in my view, this is, it has been, I have later on got involved in other startups as well. It has always been extremely educational to directly talk to the customers, potential customers of your technology, and to figure out why they may potentially be interested in what you do. This is one of those educations that I went through that I think shaped me greatly.
You know, maybe I can just add one more very quick thing to that. You know, so I think Shauni mentioned like talking to the businesses, talking to customers, and I hope the grad students were listening. Aswad did most of the work, right? But of course, Shauni kind of providing all the vision. And one thing I wanted to say, just to add to that, you know, I do think there is merit in what Milind was suggesting, in the sense that it's true that the businesses are the immediate customers, but you know, I also feel at the end of the day, it's the end user who has to pay for it. And you know, like single-use plastic, right? So you can buy this for $2, but if you are going to ask for, say, 2 times, 3 times the cost, I will willingly pay if I understand that, you know, that single-use plastic is actually not good for the environment, and maybe, okay, those extra couple of dollars are worth it. So I also think that maybe if we're all very busy, but at this stage, I mean, we are in a very, very, no need to mention that, but we are in a difficult stage in terms of many things about science technology. So at some point, advocacy does help in the most gentle way, but I think that it can play a role in adoption of technologies, because the end user really wants it. I mean, I don't want a building which does not have radiative cooling. I don't want to rent that apartment, right? I think those things can also drive change in the positive sense. So I do think that that does help. Yeah, I think Ashraf and then...
I can add a quick thing that maybe one of the things our students can go do is to go to city council meetings. Because it was just like Professor Fan, it was an interesting experience for me. I also work on agrophotovoltaics along with Professor Barmel. And I never understood that why they are so opposed to it. Here is my technology. It will give you an income throughout the year. It's making your life better. Everything is good. Why you are not interested? And I realized that in that meeting that they don't trust anything. It's a cultural divide. Anything that people with advanced degrees say, they don't trust it. Because what happens is that often they will build all these things and then they will walk away. And these people are left with the loans and other things. So there is a communal trust gap in terms of technology adoption. And I think this is very important that we try to understand this in that context. And going to city council meeting is always fun, because you can see that how many misconceptions can be amplified with each other.
Right, is this working? So let me add to it something. It's not a question. In a famous interview, when asked about the reasons for his great success in the beginning of 20th century, Henry Ford explained that one of the important reasons was that he was never asking the stupid customers. For example, they wanted cars with different color, and the Henry Ford's position was, sure, you can have any color under the condition that the color is black. And then he was asked, well, kind of doesn't really make sense. Well, and the response was this: if I asked one of those alternatively interesting people what they wanted, they would have wanted a better horse.
Thank you so much, Evgeny. I mean, that's very, very interesting insight. And it can only come from a very astute observer. Thank you so much, Evgeny. And let's go to the next question.
Hello. Thank you so much for the panel. So my question is not to a specific professor, so it's a general question. It's like, it seems like you guys all work with inorganic materials about nanophotonics or energy-related topics. And have you guys ever thought about like using organic materials, or do you think like any type or not specifically, but any type of organic material will play an important role in the topic that you've been working on? Not to a specific person, you guys can compete.
Well, polyethylene is organic, right?
Yes.
So you are from my group. You know we use binder, which is organic. So yeah, there are a lot of challenges. But you mean the functional part, the key but the binder is very important as well. So yeah, there are organic, which is the mainstream, and there's inorganic, which is more durable and quite more expensive. There has been a company trying to commercialize the inorganic-based technology used in space to the Earth's application. There is barrier, of course, on the cost. So we got to think about ways how to reduce the cost and make it viable for Earth's application. But the organic materials used in commercial paints are a good balance between the cost and performance. I think that's still promising to push the radial cooling paints technology to the market. So it is promising, but the question is there that we need to pay attention to. Yeah, that's my take. Thank you.
Thank you, Sholin. Peter, would you like to add to that?
Just briefly, one of the most important emerging photovoltaic technologies is called perovskites, and perovskites are typically, although not automatically, organic materials. So an example is called methyl ammonium lead iodide, and there are lead-free options as well, if you prefer. But it's a really exciting field because it's one of the fastest improvement curves in terms of technological performance as measured by efficiency of converting sunlight into electricity of almost any technology that I've seen, right? So they got above where silicon is, and silicon is like the oldest technology within the course of like maybe 10 or 15 years, which is unprecedented.
Yeah, and I just wanted to add that the organic materials have been part of optoelectronics and optics for a long time, and they also hold potential even for quantum applications. So one of the things people are looking at is like quantum emission, and again, the material space is very broad. So people are investigating all materials, including organics, that are very promising for multiple applications.
And a small addition, it's also the place of the biggest fraud of scientific history.
Oh, yeah.
So for the young folks, they should read about the organic laser and other things when you go back. It's going to be a fun story to read about. That's what Evgeny's comment was. What I'd like to do is, we are having a good time talking about energy, but remember we have a couple of other things that we also wanted to squeeze in before we leave today. And I do think it's necessary to definitely talk about quantum. There are multiple reasons for that. So quick context, we have our distinguished guest who has come to the Midwest, and as many of you know that there is a huge investment from DARPA as well as our neighbors in really changing the south side of Chicago. So the vision, and we don't know if it'll come true or not, is that the south side of Chicago, the steel plants and stuff, they'll actually may completely change in the future. And the quantum benchmarking program from DARPA is trying to invest in the two main technologies. One of them is topological qubits, but the other one is nanophotonics. It's the nanophotonic chip fabrication, and that might lead to some of the kind of important advancements we don't know. And being in the Midwest, I think this is a good time to be thinking about nanophotonics and quantum, right? Because we might have access to some of these technologies in the near future. But there are many challenges to be overcome. So what I wanted to ask the panel, and I'm sure the panel has thought about this includes problems like, nanophotonics by itself is not going to solve the problem. We need to interface with nanoelectronics. We have kind of experts on the panel talking about who have thought about nanoelectronics for a long time. So my question is, what are these key challenges and roadblocks that you see that can maybe transform the south side of Chicago? Is it possible? Is it not possible? How much time will it take? As I was just in a workshop, and there were a couple of skeptics, and very rightfully so, that quantum computing has been a technology that has been 10 years away for the last 30 years. So we have all of these kind of difficult questions. But at the same time, a great fab that does nanophotonics and integrates it with many technologies is really useful. So the question to the kind of distinguished panel is, where do you see the challenges, the opportunities, and how can we contribute as a community? Yeah. Please.
You want to start?
Maybe I'll put you on the spot again.
Okay.
Yes.
I think it's a very exciting time on the quantum side. And one of the very exciting things that I see is that many of the technology that one built for classical light directly translate on the quantum side. If you look at many of these companies, PsiQuantum is doing, what they are doing is in fact pushing in many ways the limit of the performance of classical light circuit in order to process quantum light. So if nothing else, it would provide a very, very interesting challenge in the optical component world in terms of what the performance needs to be. So the other thing that it would be very exciting is that it build upon also this trend of building up this photonic foundry and building up infrastructures in building photonic circuits. So those things I think are, to me, certainly there are lots of fundamental science that are also very exciting, but I think on the engineering side, those are very exciting opportunities.
Maybe I can continue and build on that. Well, I think there's no doubt, and many people agree on that, that photonics is actually the technology that's going to yield us the most immediate applications, and they are already existing, right? When people say quantum, they always say, where is your quantum computer? And my answer is always, well, quantum is not only about universal quantum computer, it's about quantum sensors, quantum communication systems, and quantum sensors are already on the market. And again, photonics is going to play and is already starting to play a key role in all these quantum technology directions. So the challenges here are, again, related to materials, related to integration, related to implementation, to scaling up and working with foundries, as you just mentioned. So you mentioned PsiQuantum. Obviously, it's fantastic what they've been doing and what they achieved. I can proudly say that we are working on an approach that can, well, if not compete, then they complement and be better in many aspects of what PsiQuantum is doing in terms of how to implement and control the quantum emissions so that we get closer to both single photon sources, but also to the sources of entangled photons and some of the more advanced, quantum states of light. And most importantly, doing that in technologically relevant platform, and well, specifically silicon nitride. And we already mentioned that it's important that the material that you're using can actually transition into industry immediately. So if you say, okay, I'm not interested and I don't need heterogeneous integration, which is hard, right? We are all talking about the emitters in one platform and waveguides in the other. If it's monolithic, it would be easy entrance to foundries. And in fact, we're already talking to global foundries to implement this. Specifically to Purdue, what I wanted to mention is that we should be leveraging all the expertise that we have in classical chip scale technology. So chip scale quantum photonics, and that's what I believe Purdue should be taking and should be put on the map for, because of the foundation that we have in chip scale technologies in a classical way, and that's what we can build on and build our partnership with ideas that we have in the lab, into the foundry, and to the customers.
Thank you, Sasha. So would anybody else like to add, or yeah?
I can add one brief point.
Yes.
I agree with what Sasha just said. So I did want to emphasize what's really exciting now is that we have had these industry scale processes that went from single transistors all the way to the billions of transistors we get in every chip today. And we can use very similar types of technologies to build photonics. And while a lot of the original impetus was on the classical side, These systems are getting to be so good that it does make sense to leverage these for quantum technologies. And in fact, that's the plan that a lot of companies have. And I think that building on that platform is actually like really impactful because like many people have this perception that optics is about creating lenses and mirrors as discrete components, but we're like way beyond that now. So building these like very sophisticated integrated systems that have the ability to do the optical components, the electronic components, it's going to be important for many reasons. It's going to be important for energy. It's going to be important for quantum communications and creating quantum internet and many like sensing applications, including life sciences and environment, et cetera. So we need to think about this as like one of the most critical platform technologies that's being developed today and really make that like a main focus of our research here.
So we are almost out of time. And what I'd like to do is, Ashraf, did you have something to add to this?
Maybe just one thing is that maybe because I don't work in this area, that there is probably a perception problem in this field that sometimes there are results reported in newspaper or in press releases that then subsequently others people debate or say that they are not repeatable, or so this is this causes confusion in the community. That is the field really moving forward, or is there sort of periodic bursts which sort of are not being sustained? So I think collectively the community needs to do some extra work in terms of creating a more uniform way of communicating the results to the public, because there is so much expectation that if the expectation is not satisfied, then there will be a big problem in terms of funding and all downstream.
Completely agreed with that. So, Shulin, please go ahead with a very brief comment. We are almost
very brief. Yeah. Yes. So I don't work on the quantum devices, photonic devices, but my appreciation of the quantum nature of a photon comes from a heat transfer researcher perspective. We look at the particle, how photons interact with the phonons. And, through material, how can we manipulate the frequency and their scattering through material and the nanostructures. So we do use quantum mechanics. That's needed every day to understand photon. And for example, combined photon-phonon particle is called the polariton. It's very important these days for the heat transfer community. So okay, that's all I want to add.
Thank you, Shulin. So what we will do is this is coming close to the end of our session. So I have to confess that a couple of the questions I did let the panelists know these are the things I'm thinking about. I'm going to ask you, but I will never let anybody go without putting them on the spot, because it's very rare that we can get their real deep insights. And so for the final question, I'd like to go through all of you one by one, and I'd like to ask just one quick question. Let's say that you were a venture capitalist, or let's say you were investing some of your own money, and you had to pick just one technology, one and only one, that you think would be important in the next 5 or 10 years. Need not be necessarily important in terms of really creating a billion-dollar industry. It could just be, there's a new theorem that's just around the bend that nobody's seeing, but, it turns out this community can actually do it, that can really propel things. So it could be really interesting knowledge, or once Mark mentioned this term that I really like, enduring knowledge. So what is that one technology or scientific problem where you think enduring knowledge could be created very soon? Right? So, and you have to pick one, right? That's the difficult part. So, and we would like our panelists to kind of tell us briefly which is the one thing you pick, and as quickly as possible. Maybe Sasha's already picked one. Wonderful.
Well, I picked it a long time ago, and I trust my husband, so... So I would, as a venture capitalist, I would I would say, yeah, make this monolithically integrated silicon nitride single photon sources, because I've been involved with Quantum Economic Development Consortium for many years that now host, I believe, like 300 plus companies. And the devices that they mostly need and would need for their needs in, sensing, communication, and computing, single photon source, well, together with single photon detectors, are on the very top. So we will have customers.
Wonderful. Thank you, Sasha, for taking the lead. For those of you who were interested, silicon nitride single photon sources. So thank you, Sasha. So who would like to go next? Thank you, Shauni.
Yeah, I'll next. I think AI for simulations.
Okay.
Yeah. I think simulation has been around for a long time. And there have been a lot of good, but in a way, somewhat incremental changes over the years. Mm-hmm. And the presence of AI probably is going to change that.
Okay.
And to see something very, very different.
Wonderful. Thank you, Shauni. So who is going next? All right, Shulin put his hand first before you put your mic up. Yes, Shulin, go ahead.
So just simply, we love to put the ultra-wide panes on buildings and cars. So by the way, we are also developing AI tools to accelerate the design. So that's well kind of aligned with the goal, overall goal for what we are doing. Yeah.
Wonderful.
Thank you.
Great. Thank you so much, Shulin. Peter?
Okay, so I'm going to make a point, which is just that as a venture capitalist, you always have to understand valuation. So in order to make an investment, you have to understand, is this thing currently priced correctly? Is it underpriced? Is it overpriced? So I would say that basically what you're asking is what technology is completely undervalued relative to where it should be valued in society, right? So is that a fair interpretation of your question?
Let me rephrase it then, all right? Let me rephrase it. Peter, you are taking all your money, everything in the bank, and putting it on one technology tomorrow morning. What would that be?
Right.
What do you believe in?
But then the point is, you have to know how much you're getting out of that, right? Like, so I'm saying if I can buy like Apple stock for $1 a share, I'm putting all my money into that. But I can't. But I can't. So I'm saying, like, with these early stage startups, what I'm really looking for is like, what is the likelihood of success of the technology, and what's like the growth path of the technology? Right. Is this going to be like a global adoption, or is it just going to be local in specific regions? So from that perspective, I think actually radiative cooling is one of the most promising markets today. And there's two reasons. So radiative cooling is a very, very low-cost technology to operate. It's essentially operating, quote unquote, for free, unless you add extra bells and whistles. But then second, it responds to the global mega trend of increasing heat islands and higher temperatures like worldwide. And we've experienced that not just in West Lafayette, but everywhere. And so in order to keep our cities cool and our people comfortable, and even other entities like livestock and so on, we need to have like cheap and effective ways to keep temperatures under control. So I can see that there's like easily like a many multi-billion-dollar market, and many of the technologies are just getting off the ground.
Great. Thank you so much, Peter. And Professor Alam?
I don't have a lot of money, but if I did, I will just invest in these three.
Wonderful. So as they say, and I remember Evgeny telling me once that you don't bet on the horse, you bet on the jockey. So you bet on the three people and what they are investing in, and that's the right way to do it. So with that, I'd like to thank the audience for your time. It's a real pleasure to have you here, and I want all of us to thank our distinguished panelists. Thank you.